The amplitude of the answer to that math equation increases. How do two hydrogen atoms bond together to form a bond? In the previous video, I talked about the linear combination of atomic orbitals. If you want to watch that, I've got a link down below. You should probably watch that before watching this one, as it gives you the background necessary. At the end of the last video, we went through like a physics type example where we added two waves together constructively and destructively through constructive and destructive interference. And adding two orbitals together is really kind of the same thing, because remember, orbitals are just answers to complicated math equations. So if we're going to add orbitals together, it's going to look a lot like adding two waves together. So the first thing that we would do is we would add these two waves together constructively. What does that mean? We would overlap these waves such that they are perfectly in phase. The two phases of the two hydrogen atoms will overlap, form a region where there is constructive interference. What does that mean? In the constructive interference, we saw that the amplitude of the resulting wave increases. So the resulting orbital will have an increased amplitude here in the center region of that new bond. So this is where the new hydrogen bond will form. The two electrons will be in this new bonding orbital. Now remember, orbitals are just answers to math equations that tell us the probability of finding an electron, a volume of space within which it is probable to find an electron. So in this constructive interference, the region between the two nuclei had its amplitude increased because of this constructive interference. So it is now more likely to find the electron in that volume of space between the two nuclei. This is the bonding of those two nuclei. It is now more likely, the electrons are more likely to be here than they were before. So this is the bonding orbital. We also call it the sigma orbital. So what is a sigma bond? Two orbitals, which are two complicated math equations, combined constructively such that the amplitude of the answer to that math equation increases between those two nuclei, showing that it is more probable to find an electron in that volume of space. The sigma bond is the constructive interference, the constructive overlap of two atomic orbitals. But that can't be the whole story, because linear combination of atomic orbitals says that the number of orbitals in has to be the same as the number of orbitals out, and so far we only have one molecular orbit. We already did the constructive interference of the two orbitals, so now we need to look at the destructive interference of the two orbitals. That means we take these two orbitals and we subtract one from the other. How do you subtract an orbital? Remember, orbitals are just answers to math equations, so we can subtract two math equations from each other by taking one and adding the negative of the other. We take one hydrogen orbital of the positive phase and we overlap it with one hydrogen orbital of the negative phase. Adding a negative is the same as subtracting. Now we have a volume of space between the two nuclei where we have completely out of phase overlap, completely destructive overlap of these two orbitals. What's going to happen to that volume of space between those two nuclei then? We're going to end up with a situation where we have the two nuclei and the volume of space between the two nuclei is going to collapse to zero. We're going to end up with a situation like this. Here, right in the middle, we have a volume of space perfectly oriented such that the answer to the math equation is now zero. That is a node. There is zero probability of finding the electron between those two nuclei. We call this the antibonding orbital, or the sigma star. Here, what I want you to see is we followed all the rules of the linear combination of atomic orbitals. We started with two atomic orbitals. We ended with two molecular orbitals. We got those two molecular orbitals by taking the atomic orbitals and combining them constructively and combining them destructively. This can all be represented in a picture that you're probably more familiar with. If we have a hydrogen atom with its one electron and a second hydrogen atom with its one electron, we can combine these two orbitals constructively to make a molecular orbital that is lower in energy, and we can combine these two orbitals destructively to make an orbital that is higher in energy. The lower energy orbital is the sigma bonding orbital. The higher energy orbital is the sigma star antibonding orbital. Now we know what this means. The sigma star bonding orbital comes from the constructive overlap of the orbitals, and the antibonding orbital comes from the destructive overlap of the atomic orbitals. Now that we have the molecular orbitals constructed, we can add the electrons to those molecular orbitals. We started with the two electrons in the atomic orbitals, so we have two electrons to add to the molecular orbitals. Finn's rule, Aufbau principle, Pauli exclusion principle says that those two electrons will end up in the lowest energy orbital. That's all the electrons that we have, so there'll be no electrons in the antibonding orbital, which is good because we didn't want to raise the energy of the system anyway. The whole goal of bonding was to lower the energy of the system. Now these two electrons are in a sigma bonding orbital, and they are more stable than the individual atomic orbitals, the individual electrons of the individual hydrogen atoms, and so H2 is a more stable molecule than two individual hydrogen atoms. We can do the same thing with p orbitals to make pi bonds, but I'll do that in a separate video, which I will link below.
I'm glad you're here with us for this training today. Check out these other videos in my playlists to see if there's anything else that can help you level up your ninja levels even further. As always, don't forget to like and subscribe.